Welcome. Today, we are going to pull back the curtain on a secret tool scientists use to make sense of all that conflicting research you see flying around. It's called effect size, and you can think of it as a kind of universal translator for science.
All right, let's dive right into a problem that I'm sure you bumped into before, probably while scrolling through the news.
You see a headline, right? New diet works wonders. But then, maybe a week later, another study pops up that says, nope, it does absolutely nothing. So, what's the deal?
This kind of thing happens all the time in science. Study A finds a significant result, while study B finds nothing. It creates so much confusion and makes it really hard to know what to actually believe. But what if there was a way to cut through all that noise? Well, turns out there is. Scientists have this powerful technique called a meta-analysis to solve this exact problem, to find the clear signal hidden in all the static. And this whole process, this whole amazing technique, it really hinges on one simple but totally brilliant concept, the effect size.
Just think of effect size as a universal yardstick. It's not just telling you if something had an effect, it's telling you how much of an effect it had. It measures the magnitude, the sheer size of a finding, no matter how the study was designed.
And that is absolutely the key. Because the effect size is standardized, it gives us this one number that we can actually compare across a bunch of different studies. It puts everything on a level playing field.
But studies collect all sorts of different kinds of data. So to make this all work, we actually need a few different kinds of effect sizes to act as our translators. Let's take a look at the main ones. First up, what do we do when a study is comparing averages? We're talking about things like average test scores between two different classrooms or blood pressure in a drug trial versus a placebo.
For that, we use a tool called the standardized mean difference. Now, it sounds a little technical, but the idea is actually super clever. It takes the difference between the two group averages, and then it adjusts for the overall variation in the data. And that one simple step just strips away the original units, so it doesn't matter if it was points or pounds or millimeters of mercury. All of a sudden, you have one universal score you can compare anywhere.
Okay, but what if the data isn't a score on a scale? What if it's a simple yes or no? For example, did a patient survive after getting a new treatment? Or did a part fail a stress test?
In that case, we translate the results into something called a risk ratio, or an odds ratio. This basically tells us how much a treatment changes the probability of something happening. Did it double the chance of survival, or maybe cut the risk of failure in half? Again, it gives us a really clear, comparable number.
And finally, what about research that isn't comparing two groups at all, but is looking at how two things are related to each other? Like, does more time spent studying actually lead to higher exam scores?
For these situations, the correlation coefficient, which we usually just call R, is actually the effect size itself. It already gives us the strength and the direction of a relationship on a nice standardized scale from -1 to +1, which makes it super easy to compare across studies.
So we have our universal translators. Awesome. But there is another really crucial piece to this puzzle. See, not all effect size estimates are created equal. Some are just, a lot more trustworthy than others. Just take a look at this table. As the sample size, that's the number of people in the study, goes up, the variance goes down a lot. And variance is really just a statistical way of saying uncertainty, or the fuzziness of our result. Look at that. Just going from 100 to 400 participants cuts our uncertainty by a huge amount.
So here's the big takeaway. Bigger studies, the ones with more data, give us a much more precise, and because of that, a more reliable estimate of the true effect size that's out there in the world.
It's kind of like focusing a camera lens. A small study gives you a blurry image, with a wide range of possibilities for what's really going on. But a large study, that gives you a much sharper picture, narrowing down exactly where that real effect truly is.
Okay, so we've got our translators, the different effect sizes, and we understand that precision is key. Now, let's see how this all comes together to turn that scientific chaos into some real clarity.
And this right here, this illustrates the real magic of the whole thing. Because these are all standardized universal translators, we can even convert between them. You can literally take a result from one study that was expressed as an odds ratio and turn it into a standardized mean difference so you can compare it directly with another study. It is incredibly powerful stuff.
So the whole process of a meta-analysis becomes pretty straightforward. First, you gather up all the studies on a topic. Then you translate each one into that common effect size language, and then, this is the most important part, you combine them. But you give more weight, more influence to the bigger, more precise studies. And from all that, you get a single, weighted average summary effect.
And through this whole process, we can finally see the big picture. We move past all the confusion from individual studies and start to understand what the entire body of scientific evidence is actually telling us.
So the next time you see those conflicting headlines, you'll know the secret, right? You'll know the answer isn't just in one study. It's in combining all of them. It's a powerful reminder that in science, one study is just a single piece of the puzzle. It's never the final picture. So the real question is, now that you know how to see the whole board, what puzzles are you going to be able to solve?